All right, try to make that a little less blue on the screen, but hopefully that's not too bad. All right, so we're up to number 4 on the study guide here. I did talk a little bit about compressional waves or longitudinal waves with you in the previous video, but we're gonna talk about that here in number 4 as well. So just looking back at number 4, you can see that there are some words we've seen before. Wavelength. The wavelength is going to look a little bit different here in a compressional wave because there's no crests and troughs. Instead, there's what we call compressions and rarefactions. So when you draw a compressional wave, there's a couple things you could think of. You could think of a slinky, where you're pushing the slinky like this, and the slinky's not going to make crests and troughs. It's going to sort of send a wave through the slinky. Imagine you're taking your slinky, you're going back and forth in your hands. So the slinky might look like this, where there's areas that the slinky is really close together, and then there's areas where the slinky is further apart. Okay, so we could think about it like that. And so the area where it's all close together is what we call a compression. Right? It's pressed together, pressed. And then the other side, the part that's far apart, where it's less likely to find particles because they're spread out, we call a rarefaction. Okay, so think about it, right? Pressed together versus rare, right? There are less of them in the same area. It's rare to find them. And so a compression and a rarefaction are just like the crest and the trough of this type of wave. Instead of it looking like that, it looks like this. And so the same thing that we've done with wavelength, where we measure from crest to crest, the same thing would be true here, except we're measuring from compression to compression, or from rarefaction to rarefaction. Either way, that's the wavelength. Okay, so those are the characteristics of a longitudinal wave. A longitudinal wave needs to travel through a medium. Needs to travel through a medium. It moves by knocking particles into one another. Okay, sometimes it looks like that original drawing where we have lots of air particles or water particles close together. That's our compression. And then there might be areas where they're more spread out. Might be areas where we have another compression. Areas where things are spread out. Areas where we have another compression. And so again, we have a compression, a compression, a compression, and some rarefactions. So the characteristics here is that it needs to travel through a medium. Instead of crests and troughs, it has compressions and rarefactions. And we're going to look at an example of that as it relates to sound coming up in the next video. Okay, so on the other hand, we have a transverse wave, which has those characteristics we talked about in the last video. It has crests, troughs, and we can measure the wavelength from crest to crest. Another big thing to think about when we're comparing longitudinal waves and transverse waves is that on a transverse wave, the wave is moving in this direction. But the particles that make up this wave are actually going up and down. Okay, so we get this perpendicular angle here, where in order to make this type of wave, you disturb the substance going up and down, like a drop of water into a cup. Flat, perpendicular. But a longitudinal wave, the wave is moving in this direction, and the way that the disturbance is happening is also moving in that direction. They're moving parallel to one another. okay? And so in order to make that type of wave, you could think of like what a speaker does. Speaker is bumping like this, and it's pushing wave of sound that way. The next question, how does amplitude affect sound? We're going to look at a simulation for that. So I'm going to pause here, and we'll pick it up again in another minute. We're back, and right now we're going to be looking at what a sound wave might actually look like if we could see the air particles moving. Okay, so this is going to make kind of annoying sound. I'll mute that in just a second. But basically, if we press play, we can see nothing happens right now except for that little wave that's moving through. Right? Little wave that's moving through these particles. Okay? You can see it. It's a compression moving through the particles. Moving through the particles. And that's what sound would look like. But this sound, it's not very loud. So if we were to make that sound louder, we can see how that looks different. Okay, so you see that compression moving through. All right. Thinking about how that might look different than when the sound is really low. And I muted the sound so you don't hear it. Okay, so that's a soft sound. And this is a loud sound. So what we should be noticing here is that we have a real thick compression. There's a lot of particles that are getting compressed. There's a greater amount of them that are in that compression. Compare that to when we have a soft sound, there's only a small amount of particles that are part of that compression. Okay? And so this relates to the volume of the sound. And what that actually is the amplitude of this type of wave, the compressional wave. The amplitude relates to the loudness. The higher the amplitude, the more compressed it's going to be. Okay, this is a lot like with a transverse wave. The higher the amplitude, the taller the wave is going to be. Okay, but this is for a longitudinal wave. Now, if we compare what happens when we change the pitch, right, a low bassy sound versus a high pitched sound, they're also going to have some differences here. So if I just pause this real quick, and I'm going to make the loudness medium, and I'm going to move the pitch from low to high. So first we have a low pitch. This is like a bassy sound. And we're just going to kind of look at what these waves look like. And we'll compare that to a high-pitched sound, a squealy sort of sound. Okay? So we're going to flip back to the other page and we'll talk about what we saw here. So be back on the other side. Okay, so the big things that we saw in that simulation there is we saw what a longitudinal wave looks like. Sound moves in longitudinal waves. You can see we had compressions, rarefactions. We saw that amplitude affects sound, right? The higher the amplitude, the more particles are going to get compressed together, which is going to relate to the volume or loudness of the sound. Okay, so basically we have two examples here. We've got we have this example of a wave, you can see we've got a bit of a compression there and a bit of a compression there. This sound would not be as loud as a wave that might look like this. Okay, so what we see here is that there's a greater number of particles in the compression area, and there's a lot fewer particles in the rarefaction particle area. And then again, we have a big amount of compress. This is about the amplitude, which affects the volume or the loudness. Now, on the other hand, we had pitch, and pitch is related to how low or high the sound is, just like I did with my silly little voice there. So the pitch, we saw, it changed the frequency. When the frequency changed, the pitch changed. And so when we looked at this word earlier, frequency, we said that wave would have a higher frequency than that wave because there's more crests per second. Now, in sound, we don't have transverse waves, we have compressional waves. So what does that end up looking like? It ends up looking like more compressions per second, okay? And that's gonna take me a long time to draw, so we're just gonna kind of go back to that visualization again real quick, and I'll sort of try to talk you through it as we look. Okay, so what we're looking at is frequency. You can see right now we have a high pitch, and so therefore we have a high frequency. We've got lots of compressions. Okay, there are a lot of them happening in the same period of time that this happens. Okay, we go to the low one. And we're going to see that these are going to be further apart. They're going to take longer from compression to compression. They're less frequent. They have a lower frequency. Okay? And so frequency controls the pitch, the high or low sound, and amplitude controls the volume. All right? So that's sound waves in a nutshell. We're going to be back with another video ASAP.